During this session, again I will be discussing a few other numerical exercises, and I will not be just concentrating on acceptance sampling. These exercises will be on quality control, reliability, as well as quality with experimental design. So, these three topics we have already gone through. Now, again there will be 8 exercises, and I will be explaining, I will be discussing all these 8 problems or 8 exercises one by one. Now, let us talk about exercise 1, that is the first one. In a piston assembly, the specifications for the piston diameter are 12 plus minus 0.5 centimeter. Is it okay? So, that is the tolerance range, and those for the cylinder say the diameter are 12.10 plus minus 0.4 centimeter. Okay. Assume that the natural tolerance limits coincides with the specifications. So, if it happens, obviously we are assuming that that the process capability ratio is 1. That means the process is just capable. A clearance fit is required for the assembly. You know that under what conditions we say that a fit is considered to be a clearance fit. What proportion of the assemblies will be non-conforming, assuming a normal distribution of the piston and cylinder diameters? Is it okay? So, that means the central limit theorem holds. Clearances more than 0.8 centimeter are undesirable. Is it okay? So, if it is more than 8 centimeter, the condition called oval may occur, and that is to be avoided. What proportion of the assemblies will not meet this stipulation? So, this is the question. So, this is related to a particular topic we have already covered under process capability, and process capability study is closely linked with the quality control. So, directly or indirectly it will have a bearing on the quality control, and here the particular topic we will be referring to, that is setting tolerances and the specifications of the assemblies when the individual component tolerances are specified. So, this is the domain, and we will just explain that against this particular exercise what are the solution steps. Assume that the specified tolerances are proportional to the size of the nominal dimension. Okay, so, that is the first assumption we make, and many a time this assumption holds. The mean of the difference between the cylinder and the piston radius, is it okay, is 0.05 centimeter. That means you know, the piston will have an outer dia, and the cylinder will have say the inner dia. So, for the clearance for the clearance fit, what is the condition to be satisfied? That means before you do the assembly, that this condition is that that the inner cylinder dia must be greater than the outer say the shaft dia or the piston dia. So, the standard deviation of the cylinder radius is obviously 0.2 by 3. It's clear, right? And so, that is 0.067, while the standard deviation of the piston radius, is it okay, that is 0.25 by 3. Is it all right? So, that means what we are assuming, that the upper natural difference between upper natural tolerance limit and lower natural tolerance limit divided by that is the 6 sigma. That means that is means the natural tolerance limits. The first one is the upper tolerance limit minus lower tolerance limit, or the upper specification limit minus lower specification limit divided by 6 into sigma. That means it is essentially the actual spread. Okay, that means the difference between upper natural tolerance limit and lower natural tolerance limit, we are assuming it to be say just 1, right. So, the process is barely capable. So, obviously, this is 0.2 by 3, right, and this is 0.067, that is the standard deviation of the cylinder radius, and the standard deviation of the piston radius is 0.25 by 3, that is 0.083. So, the variance of the difference between the cylinder and the piston radius, that is you add the sum of the squares of the individual the standard deviation, that is 0.067 square plus 0.083 square, that is 0.01138. So, what is the standard deviation? That is the root over 0.01138, that is 0.1067. Is it okay? So, the sigma is known between the difference. The standard normal value at 0, that is z equals to 0 minus 0.05 divided by 0.1067, that is minus 0.47. So, using the normal tables, okay, the proportion of non-conforming assemblies is 0.3195. Is it okay? That means what you are trying to do, you are getting the difference between the diameter of the shaft and diameter of the cylinder and diameter of the shaft or the piston. Is it okay? And what you are assuming that this difference is also normally distributed, and for a clearance condition to hold, that means it must be greater than 0. So, that is why against 0 you compute the value of z. Using the normal tables, the proportion of non-conforming assemblies is 0.3192. Is it okay? That means the area under the curve, say the less than that particular value, that is z equals to 0.47 minus 0.47. So, that area under the curve beyond minus 0.47, that is the value of z, you refer to the standard normal table, you get an area of 0.3192. The standard normal value at 0.8 is z, 0.8 minus z equals to 0.8 minus 0.05 divided by 0.1067. We are assuming that the sigma, the value of sigma does not change. So, this value is 7.03. So, if you refer to the standard normal table, you will find that the proportion of assemblies not meeting the stimulation is negligible. Is it okay? There is hardly any area beyond this value, that means 7.03, the value of z was 7.03. Okay. Now, let us move to exercise 2. Suppose 3 sigma control limits are constructed. You know what is the 3 sigma control limits, and this so the 3 sigma control limits are constructed, or the control charts are constructed for the average temperature in a furnace. Is it okay? So, that is the quality characteristic of interest. Sample of size 4 were selected with the average temperature being 5000 degrees Celsius. That means, it is a variable control chart, and the standard deviations of 50 degrees Celsius. Find the C sigma control charts. Suppose that rules 2 and 3, you refer to this, there are 5 specific rules for out of control conditions we have mentioned. So, the rule 2 and rule 3 you refer to. Suppose that rules 2 and 3 are used simultaneously to determine out of control conditions. What is the overall probability of a type 1 error assuming independence of the rules? Okay. So, that is the second question. The third question is, approximately how many samples on an average will be analyzed before detecting a change when rules 2 and 3 are used simultaneously? Then we go to question number 4. If the process average temperature drops to 4960 degrees Celsius, what is the probability of failing to detect this change by the third sample point drawn after the change? And the last question is, what is the probability of the shift being detected within the first 2 samples? So, these are the typical problems you come across related to control charting. Now, the central line on a chart for the average temperature is obviously 5000 degrees Celsius, right. The standard deviation of the sample mean, that is sigma x bar, is equals to sigma upon root n, that is as per the central limit theorem. So, the sigma is 50 that is given and n is 4. So, it comes out to be 25. So, 3 sigma control limits are 50 plus minus 3 into 25, that means 4925 comma 5075, fine. So, we know what are the control limits. Assuming the 3 sigma control limits, the probability of type 1 error using rule 2 was previously found to be this one, 0.003048. Okay. Also for rule 3, the probability of type 1 error was found to be this one. Is it okay? So, you know what is rule 1 and what is rule 2, what is rule 3. So, you please refer to rule 2. We have already computed the what is as per the, if you follow the rule 2, that means the 2 out of 3 consecutive the sample points plotted on the same side of the central line, but the plotted beyond 2 sigma warning limit. Is it okay? So, that is basically the rule 2. So, what is this probability? Already you have computed. Similarly, rule 3 is the 4 out of 5 consecutive sample points plotted beyond 1 sigma control limits on the same side of the central line. So, corresponding probability is this one, we have already computed. Assuming independence of the rules, the probability of an overall type 1 error. So, the overall type 1 error, suppose you deal with I number of such out of control rules. So, what is the expressions for overall type 1 error? That part also we have discussed. Okay. So, you refer to that particular formula and you just apply that formula with respect to just the two rules, rule 2 and rule 3. So, ultimately you get an expression of alpha as 1 minus, this is a product term, is it okay, pi I equals to 1 to 2, and the corresponding value is, that is the type 1 error probability with respect to 2 and 1 minus of that, okay, 1 minus alpha 1 into 1 minus alpha 2, or here 1 minus alpha 2 into 1 minus alpha 3. Is it okay? So, alpha 2 and alpha 3 already you have computed. So, ultimately the overall type 1 error probability is 0.008368. Since the overall probability of a type 1 error using rules 2 and 3 is this one, that is this value, on an average, the number of samples analyzed before an out of control condition is indicated is 1 upon this one, that means 1 upon alpha. So, that means 1 upon overall type 1 error, say the probability. So, that is around 120. Is it okay? So, points. Then the next one, so if the process average drops to 4960. So, what you need to do, that means against the standardized normal values at the control limits are, again you calculate actually 4960 and this is 25, that is 4.60, and J2 is 1 minus 1.40. Using the standard normal tables, the area above the UCL is, that is beyond 4.60 is up to 4 decimal place, it is 0. So, it is absolutely you may assume it to be 0, and that below the LCL, that is minus 1.460, that is 0.0808, that means 8.08 percentage. The area between the control limits is 0.9192, which is the probability of non-detection of the shift on a given subgroup. That means this is the probability of making type 2 error. Now, the probability of detecting shift on the first subgroup is this. Next, the probability of not detecting the shift on the first group and detecting on the second subgroup is 0.9192 into 0.0808, that is 0.0743. Similarly, the probability of non detecting the shift on the first two subgroups and detecting on the subgroup is this one. So, all sorts of the possibilities you have to explore, and then you get the probability of failing to detect the change by the third subgroup point drawn after the change, that is 1 minus, this is the overall, but till means you need to you can detect the shift by the third sample that already you have computed, that is 0.2234. You follow this this particular the steps. I am sure that you will understand fully, and ultimately the probability of non-detection, okay, that is 0.7766. Using the computations, all these computations which you have carried out, the probability of the shift being detected within the first two subgroups already you have computed, that is 0.1551. Is it okay? So, we have answered to all the questions, okay, set in this particular exercise. Next we move to exercise 3. Consider a 2 to the power 4 factorial experiment. We have already discussed what is an factorial experiment. So, 2 to the power 4 means we are considering 4 factors and each factor at 2 levels. Set up a table of the coefficients for orthogonal contrast. We have already referred to the orthogonal contrast. So, please refer to my the lecture sessions on orthogonal contrast. It is a part of the topic called the quality by experimental design. Write down the contrasts for estimating the main effects and the two factor interactions. If the four-way interaction effect is ABCD is not significant, and that is your assumption, okay. Use that as a basis to confound the design into two blocks. So, this is the problem. So, you go through the contrast ABC, you apply this formula, is it okay? There are 4 factors, is it okay? That means if you say A, that means out of these 4 factors, the factor A is at the high level, whereas the other 3 factors at the low level. So, this will you follow this formula for 2 to the power 4 factorial experiment. The general formulation is given. To confound the design into 2 blocks, we take the treatments with a positive sign in the contrast ABCD and put them in block 1, and the treatments with a negative sign are put in block 2. So, this is the rule we follow. So, the treatments in block 1 will be 1 AB, AC, BE, AD, BD, CD and ABCD. So, this is BC, AB, AC, BC, AD, BD, CD and ABCD. And the treatments in block 2 will be A, B, C, ABC, these are all negative values, D, okay, ABD, ACD and BCD. Is it okay? So, now you get all the values, and then you create this table, and this is the contrast AB, C, AC, BC, D, AD, BD, CD. Is it okay? And here you have this one, so the 1 AB, C, AC, B and C. Is it okay? So, this is the solution. You just go through this table, right? And so, this continuing, in fact this table continuing. So, please refer to this table, and I am sure you will understand all the steps. Is it okay? So, and you refer to my the lectures, and plus the portion which you are in the topic of say the quality by experimental design. Now, let us move to exercise 4, the 4th one. So, here the patient satisfaction is a key response variable in evaluating the performance of the healthcare facilities. Is it okay? So, that is the key response variable for such a system. The impact of 3 factors at 2 levels each on patient satisfaction is to be evaluated. So, what are the factors? So, first factor is referred to as the factor A, is the frequency of visit by the nurse. Is it okay? That is factor A. Once every 2 hours, that is level 1, or once every hour, that is level 2. Factor B is, that means it is the level -1 and it is level 1. Is it okay? That means it is the low level, it is high level. Factor B is the amount of time spent by the doctor with the patient. So, 10 minutes per day, it is level -1, that means it is considered to be low level, or 20 minutes per day, it is considered to be high level, that is it is denoted as level 1. Okay. So, Factor C is the type of food provided, that is the meal selected by hospital management, is it okay, that is level -1, that means the low level, or the patient provided choice, that is level 1, is it okay. So, these are the assumptions and these are the values, okay. So, we have defined what are the factors, and we have also defined say the levels in each factor. Table shows the responses measuring patient satisfaction on a 50-point scale, is it okay. So, essentially this is a subjective factor, and you know what you try to do in many a time when you deal with the subjective factor. So, you need to go for making it objective. So, the scaling technique you may use, okay. Many cases we follow this. So, here on a 50-point scale, each patient will be asked to assess his or her satisfaction level. The larger the value, the higher the satisfaction level. So, that rule also you have to specify when you go for the scaling technique. The patients were randomly assigned to each treatment, is it okay. So, random assignment parts also you know, like say we have already explained what is so how to apply the principle of randomizations in experimentation. Find the main effects and the interaction effects. Find the sum of squares for each of the main effects and the interaction effects. At the 10% level of significance, which effects are significant, interpret your inferences, okay. So, what you try to do, that means all the treatment combinations, is it okay, that means 3 factors we have considered, and what are those treatment combinations, already we have explained. So, these 8 treatment combinations you consider, and the patient satisfaction level, that means there are the 3 replications you have, that means 6, 8, 9. Similarly, for these particular treatment combinations you have 10, 16, 15, right. So, these are the possible say the satisfaction levels you get against each treatment combination. Then we have a 2 to the power 3 factorial experiment with 3 replications. So, you just go through, I have already mentioned these are 3 replications. So, 3 values against each treatment combinations you have collected, or 3 data points. The main effect of B is found from this one, the main effect, is it okay, that is the formula you use, right. And ultimately what you find, that this is basically 3 into 4, that means there is a positive one, that those effects which where you will find this is all positives and this is all negative, is it okay. So, you apply the formula, you get a value of B 3.333. Similarly, the other main effects and the inter effects are found and shown in the table, is it okay. So, you just refer to that particular say the formulations and in factorial experiments, and you have the data and you compute those values. The sum of squares is found as this, okay, sum of squares. Similarly, the sum of squares for all the main effects and inter effects is found and as shown in the table. The total sum of squares is calculated is this, okay. So, again you are applying the formula. The error sum of squares is found by subtraction and is equal to 169.333. That means ANOVA table you constructed. At the 10% level of significance, the corresponding the value of the F statistics is this one, that is 3.05, is it okay, at 10% level of significance. Comparing the F statistics with this value, we find that the interaction effects of AB, AC and ABC are significant. The F values associated with the mean effects of A, B and C also exceed the critical value. However, since the interaction effects are significant, we do not make any definite inferences on the main effects. That means, whenever you construct the ANOVA table, now you have to interpret the values which you get as a part of analysis of variance, and such explanation is to be given. So, this is the typical example, please go through them. So, the sources of variations are like this, the effects you calculate, degrees of freedom you all know, that means the total degrees of freedom is 23. Sum of squares you compute, all the formulations are known. Then the mean square, that means the sum of squares divided by the degrees of freedom. So, you get the mean squares, and then you have the F statistics you compute. Is it okay? And then you interpret them. Now, next you move to exercise 5. The following parameters corresponding to a 3-parameter Weibull distribution. That means this particular exercise is related to the reliability. Is it okay? So, the value of beta is 1.7. This is essentially it's a shape parameter, and the theta is the value of theta is 7,000 hours, and the T0 is 60 hours. Define the following. That means the probability that of the system that it will run for 200 hours, MTTF, the medium value of T, and the standard deviation you need to compute, and the design life for a reliability of 0.97. Is it okay? So, you apply the formula. That means when it is a Weibull distribution, RT is equals T to the power minus T minus T0 by theta to the power beta, and you know all the values over here, and you get a value of 0.9987. It is very, very high. Then similarly, the MTTF calculation, the expression also you know, and it is a gamma function. That means T0 plus theta into gamma of 1 plus 1 upon beta. So, the beta value is given, and then you calculate these values as 6291 hours, and the T medium, again you apply this formula. Okay, already it is given in the text as well as in the lecture materials, as well as I have already explained it in the lecture sessions on reliability. And so, this is the value of T median, and you calculate the variance applying this formula. Okay, and then this is the expressions, and you get a value of the sigma as a positive square root of the variance as 3.79.64. So, you just follow all the steps, and I am sure you will be you will fully understand all the steps. Okay, and this is a typical problem, and this is the expressions for TD. That means when the reliability is 0.98, what is the corresponding the life okay in hours of the given component. So, you just apply this formula, and you get a value of 957.88 hours. So, almost say 1000 hours. Okay. Now, one more exercise I will go through, that is exercise 6. So, here again it is related to the reliability. The mechanical components in an electromechanical system have a time to failure distribution that can be modeled by the Weibull distribution with a scale parameter of 500 hours, that means the value of alpha, and the shape parameter of 2, that is the value of beta. Determine the reliability of the components after 800 hours of operation, the mean time to failure, and the failure rate, whether is the failure rate increasing or decreasing with the time. Is it okay? So, that conclusions you have to make. So, what is the solution? So, RT expressions you know. Is it okay? And you know that the T is 800, theta is 500, and you get a value of 0.0773. Is it okay? So, it is very, very less. So, the mean time to failure is this, okay, theta into so the gamma function of 1 upon beta by beta plus 1. So, you get a value of 443.115, and the failure rate function is this. Is it okay? RT. Is it okay? It is like say FT by RT, capital RT, that expressions already we have derived. So, you get a value of this one, and the failure rate function clearly increases with time. Is it okay? So, that is your conclusions. Exercise 7 is related to the two kinds of redundancy, low level redundancy as well as high level redundancy. So, when we refer to say the reliability for different types of configurations, so one particular configuration is related to redundancy. So, if you incorporate redundancy in the system or in the system's configuration, what you expect that the reliability of the system increases. Now, we have already explained that what is the low level redundancy, what is the high level redundancy. So, here find what you need to do. Suppose this particular system structure is given. Find the system's reliability of the configuration shown in this one. This is figure 1 and this is figure 2. So, there will be the series systems, there will be a parallel systems, and it essentially is a combination of series and parallel systems. So, now we apply the formula. You already know that how to get an expressions for the with respect to the first system structure, what is the system's reliability. That is, it is you apply this formula, the steps are involved, and you get a value of 0.7526, and for the second system structure you get a value of 0.7923. Is it okay? So, we have already explained all these details, and exercise 8 is find the component MTTF. Find for the component MTTF necessary to provide a system's reliability of 0.95 after 120 hours of operation. Assume that the components have the same constant failure rate. So, high level redundancy, the figure is given, and low level redundancy figure is given. Is it okay? Now, you compute the system's reliability, and for the first one, and you again compute the system reliability for the second one, and you calculate the MTTF for the first one, and you also calculate the MTTF for the second one. Is it okay with the corresponding value? So, these are the 8 problems we have referred to, and my suggestion is that you go through all the exercises which we have covered against each topic, and plus definitely in course of time where there will be different kinds of assignments. So, you will go through all these assignments. So, our main purpose is, so on any topic in this particular course, so you must have say extensive the knowledge as well as an in-depth understanding of all the tools, techniques and the approaches that we have discussed.